Welcome to the deep dive. Today, we're doing a really technical exploration, getting into the architecture of autonomous reasoning systems.
Hmm.
Specifically, we're looking at deep research agents, or DR agents.
Right. These aren't just simple Q&A bots.
No, exactly. They're designed to go way beyond that, using external tools, search, browsing.
To handle really complex, multi-step research tasks. Stuff that needs planning, retrieving information iteratively, synthesizing it all.
And the reason we're focusing on this now is pretty critical. There's this persistent performance gap we're seeing.
Yeah, it's noticeable. The huge proprietary systems, think OpenAI's DR agent, Gemini 2.5 Pro DeepResearch.
They still seem to have a functional edge over the open source option.
They do.
Yeah.
And for anyone wanting to democratize these kinds of advanced research tools, well, understanding why is key.
So what are the core bottlenecks based on the research you've looked at?
It really seems to boil down to two main interconnected things. First, data quality. A lot of the open source training just lacks diverse examples, especially examples with complex logical structures, different kinds of uncertainty, the stuff that really pushes multi-hop reasoning.
So if the training data is too simple.
The agent just won't generalize. Exactly. It learns shallow patterns.
And the second bottleneck.
That's training scalability and stability. Doing reinforcement learning, RL, for these agents at scale is a massive engineering challenge.
Because you're dealing with the real web.
Right. You need huge rollouts, high concurrency, hitting real web APIs that are, well, volatile.
Latency issues, failures, inconsistent outputs.
All of that. It messes up the training process, leads to unstable policies, models just don't converge properly.
Got it. So our mission today is to unpack two specific open source approaches that tackle these problems head on. We're looking at WebShaper and WebSailor v2.
Two really cutting-edge systems.
And this isn't just a high-level overview. We're really going to dissect the mathematical underpinnings, the agent architectures, the synthetic data pipelines.
All the stuff that's letting these open source models start to close that gap.
Exactly. This is aimed squarely at you, the technical expert listening in. We'll be getting into the weeds on the architectural and mathematical details.
Sounds good.
Okay, let's start with WebShaper and how it tackles that data complexity issue. The sources talk about a pretty radical shift, right? Moving from information-driven to formalization-driven data synthesis.
That's the core idea.
Yeah.
The older approaches, things like WebDancer or TaskCraft, they were what's called information-driven.
Meaning
They'd start by searching, grabbing a bunch of information, structuring that collected info, and then getting an LLM to turn it into questions and answers.
So working backwards from the retrieved data.
Exactly. Retrospective. And that had some serious limitations.
Like what?
Well, first, the LLM generating the Q&A often didn't fully grasp the complex structures it was given. So you'd get inconsistencies, flawed logic, incorrect QA pairs.
Right. The understanding wasn't deep enough.
And second, because it started with this sort of sometimes disordered retrieval, it tended to generate redundant structures, the same kinds of simple information patterns again and again.
Which limits the diversity needed for generalization.
Precisely. The training data lacked structural variety.
Okay, so this is where WebShaper brings in the math. They call it the information-seeking task formalization, grounding it in set theory and logic.
That's the key innovation. Instead of just relying on, fuzzy text scraped from the web, they build a formal foundation. And the basic building block is the knowledge projection, or KP.
KP, let's break that down.
Okay, so the formula is VSV. It exists V and V in R text, or V in R text.
Right.
Basically tells you the set of entities you get when you apply a specific relation R to an initial set of entities V.
Okay, so E is the universe of all possible entities, people, places, dates.
Teams, concepts, anything.
Okay.
And R is a specific relationship between pairs of entities, like born in or played for.
So the example they give is Romborn.
Exactly. That projection gives you the precise, verifiable set of all entities, people, presumably born in the 1990s. It's derived formally, not just from parsing text.
And the real complexity comes when you combine these KPs, right, using logical operations. WebShaper specifically focuses on R union, the union operation. Yes, R union is essential for modeling queries with or conditions or uncertainty.
Like, find players who played between 2000 and 2010.
Exactly. That means applying the played in relation to the union of the years 2000, 2001, and so on. So RCUP.
Okay.
And the crucial insight WebShaper brings is Proposition 1. They prove the distributive law holds for R union, RS1 cup RS2, ideal allows 1 cup S2 dollar. Hold on, Proposition 1, RS1 cup, S2 $. That looks simple. Why is proving that distributive law so important for generating the data?
It seems simple, but it's actually huge for the LLM acting as the data generator. Think about it. In the real world, an agent might have to do separate searches for RS1, then combine the results.
Right, two distinct operations, potentially.
But if the LLM generating the training data had to explicitly map out that complex branching search logic for every union, it would get really complicated and error-prone.
Ah, okay.
By proving the distributive law, the system knows it can mathematically simplify. It can combine the source sets first, $1 cup, S2, and then apply the relation $2 just once.
So orgies nor other.
Precisely. This lets the agent that's expanding the questions represent complex uncertainty, the union using a single combined source set $7. It helps manage the complexity, especially when information needs to be pulled from multiple sources to satisfy that union condition.
Okay, that makes sense. It simplifies the representation for the generator agent. And how does that contrast with the intersection operation?
Intersection, right, that's for AND conditions.
Yeah.
When the target entity has to satisfy multiple conditions simultaneously across different relations.
Like, played in 2000, was born in the 90s.
Exactly. That would be $, text-born 90 source to text-born in cap. You intersect the results of the two projections.
Yeah.
So the full formal target set, T dollars, ends up looking like this combination. $2, big gab I1.
Wow, okay. That looks complex, but it's a precise blueprint for the answer set.
It is. It's verifiable, independent of how you actually find the answer.
This whole formalization process seems like a lot of upfront work, but the sources claim it gives 3 major advantages for the training data itself.
It definitely pays off. First, you get broader task coverage. Because you're building tasks from logical blocks, not just random text snippets, you can systematically create a much wider variety of information-seeking patterns.
Right, not limited by what you happen to scrape first.
Second, task controllability. You can tweak the parameters in that formal definition, the number of relations P, the number of union terms T, to precisely control the structure and complexity of the generated tasks.
So you can dial the difficulty up or down deliberately?
Exactly. And third, you achieve structural and answer consistency. Because the target answer set $2 is formally defined and verifiable, the whole reasoning structure and the final QA pair are inherently interpretable. This massively cuts down on the inconsistencies you saw in the older methods.
That structural integrity sounds crucial for effective training, especially with RL later. Okay, so we have the math. How does the system actually build these complex, formalized questions? They use something called an agentic expansion strategy.
Yes, it's an iterative process. It starts with seed construction.
Okay.
They take a big offline Wikipedia dump, crucially, keeping all the hyperlinks, which act like initial relationships. They do random walks on this graph, pull content, and feed it to an LRM to generate about 18,000 initial seed questions, Q dolly orders T.
Raw generation.
No, there's a tough filtering step.
Yeah.
They use existing systems like WebDancer, and, importantly, a model called QWQ to try and solve each seed question 5 times.
QWQ.
Question with query context. It's a verification model. They only keep seeds where at least one of the 5 attempts gets the right answer.
Ah, so ensuring the basic seeds are actually solvable.
Right. Establishes a baseline of validity.
And then this seed question, $, gets expanded iteratively.
Yeah.
Takes $ plus 1 PT. How is that complex formal logic represented for the expander agent? Set theory notation seems pretty dense for an LLM prompt.
It is. They realized raw notation wouldn't work reliably, so they created a simplified knowledge projection representation for the prompt.
How does that look?
They use special tokens at C for constants, like Berlin in 1995, Viet for variables, the things the question is trying to find, and the basic KP becomes a triplet. 6 hours R.
Okay, 6 X's R.
Where X is the target variable or constant, R is the relation, and S is the source set. And importantly, because of Proposition 1, that distributive law,
Right.
a complex R union like $6 cup S2
Right.
can just be represented with $0 being the combined set $6 cup S2. The LLM doesn't have to explicitly handle the union logic in the triplet structure itself. It simplifies things.
Got it. That makes the prompt manageable. Now, they specifically wanted to avoid problems seen in older expansion methods, like random or sequential expansion. What were those problems?
Right. Those earlier paradigms had issues. Random expansion could connect constants to other constants, like adding the fact Dynamo Berlin is a football club based in Berlin.
Which is true, but doesn't add reasoning complexity.
Exactly. It's irrelevant noise. Sequential expansion, on the other hand, risked creating shortcuts. It might connect a known constant directly to the final target variable, letting the model guess the answer without doing the intermediate reasoning steps.
Skipping the hard part.
Yeah. So to avoid both of those pitfalls, redundancy and shortcuts, WebShaper uses a layer-wise expansion strategy.
Layer-wise.
It's a controlled, depth-first kind of approach. The agent can't just randomly add any connection. It has to build outwards, layer by layer. Any new constraint must logically depend on the result of the previous layer, and it specifically targets variables.
Forcing iterative refinement.
Precisely. It guarantees that adding constraints actually increases the required reasoning depth, preventing those simple, constant-to-target shortcuts.
Makes sense. And the expander agent needs tools to do this. What tools does it have access to? There's a novel validate tool mentioned.
Right. It has a standard search tool, which importantly allows temporal filtering. You can specify years using 5 queries, filter year.
Okay.
Then there's the summarize tool. This is where the R-union concept really gets implemented.
Handling the Signavor 1 cup S$2 part.
Exactly. If the source set $6 represents a union, this tool has to visit multiple URLs retrieved for the different parts of the union, synthesize the information from all of them, and integrate it to produce a single, unified constant set representing the union result. It's operationalizing that distributive law.
Complex synthesis required there. And the validate tool, using QWQ again.
Yes, the validate tool uses QWQ for 2 crucial checks after a potential expansion step. First, a consistency check. Does the type of the new constant at C make sense given the sub-question it answers?
Logical type checking.
And second, the really interesting one, the simplicity check. They run the QWQ model on the newly formed sub-question, using only the newly added context.
Okay.
If QWQ can answer it directly just based on that new piece of info.
Then the step was too simple.
Exactly. It means the expansion didn't actually force multi-hop reasoning. It created a shortcut. So the entire proposed expansion is invalidated, thrown out.
Wait, hold on. They throw away potentially valid data. If QWQ can answer it, isn't that still a useful, solvable data point, reinforcing basic retrieval? Why enforce complexity by rejecting simpler valid steps?
That's a great question, and it highlights the core philosophy here. It's a deliberate trade-off.
Okay.
The big challenge, the performance cap, wasn't because models lacked data for simple single-hop retrieval. It was the lack of hard multi-step problems that forced generalization and planning.
Right.
Training on too many easy examples lets the model learn heuristics and shortcuts, potentially hindering its ability to develop robust, long-horizon reasoning. So by being aggressive with that simplicity check...
They're filtering for complexity.
Precisely. It acts as a structural complexity filter. It ensures the final data set is heavily weighted towards problems that demand compositional, multi-step reasoning. They prioritize the quality of difficulty over the sheer quantity of easy data points.
That's a bold move, but it seems to have paid off. Looking at the benchmarks, WebShaper using Qwen 2.572b hit 60.1 on GAIA.
Which is huge. As the paper notes, it's the only open source method documented to break 60 points at that time. It significantly closed the gap with the proprietary state-of-the-art, which was around 67.4.
And the impact of the RL phase, built on this specific data, was massive.
Staggering, really. That Qwen 2.572b model jumped plus 13.5 points on GAIA after RL refinement, from 46.6 base to 60.1.
13.5 points. That's an enormous gain from RL. It really validates the idea that this formalized data structure is particularly well suited for RL training. Why is that? Why such a huge improvement?
The key seems to be reducing noise in the reward signal for the RL algorithm.
How so?
In older methods with fuzzier data, the agent might fail a task and get 0 reward, even if its reasoning steps were logically sound, simply because the original question was flawed or the reference answer inconsistent.
Right. The data itself was noisy.
But with WebShaper's formalization, the trajectories have inherent logical structure and verifiability. So when the agent fails during RL, it's much more likely that the failure is due to a bad policy choice, not bad data.
A cleaner signal for the RL to learn from.
Exactly. A more reliable gradient. This lets the RL algorithm converge much more effectively towards a good information-seeking policy.
And we can see the complexity in the data by looking at how many tool calls are needed per task, right?
Yes. Figure 8 in the source shows this clearly. The trajectories generated by WebShaper have a very pronounced long-tail distribution for tool calls.
Meaning many tasks require a lot of steps.
Right. They show tasks requiring up to 30 tool calls, which strongly indicates genuine multi-hop reasoning. And specifically for tasks needing more than 3 steps, WebShaper's trajectories used, on average, 3 to 4 times more tool calls than baseline methods.
Proof that the synthesis methods successfully created problems demanding deep compositional reasoning.
Which is exactly what you need to train an agent capable of complex research.
Okay, fantastic breakdown of WebShaper. It really pushed data quality through formalization, but that layer-wise expansion, while controlled, might inherently limit the absolute structural complexity, keeping things somewhat hierarchical.
That's a fair point. It enforces depth, but maybe not maximum interconnectedness.
Which brings us nicely to WebSailor v2. It shares the goal high-quality synthetic data, which they call SailorFog QA v2, but it comes at complexity differently, focusing more on rich graph structures and, critically, engineering a super-stable training environment.
Exactly. WebSailor v2 takes the view that real-world knowledge isn't just deep. It's densely interconnected, messy, not always tree-like.
So, they felt previous methods, even graph-based ones, or easy-to-hard curricula, still produced structures that were too simple, too acyclic.
Pretty much. They tended towards tree-like or DA-like directed acyclic graph logical structures. WebSailor v2 argues that doesn't fully capture the complexity of real knowledge graphs where dependencies can loop back.
So how did V2 generate more intricate nonlinear structures? How did they get cycles into the logic?
Their key structural improvement was to actively seek out and create dense connections between nodes in their knowledge graph representation.
Yeah.
They intentionally generate cyclic structures.
A cycle being A connects to B, B to C, C back to A.
Something like that, yeah. These cycles represent complex interdependencies, forcing the agent to reason through constraints that loop or influence each other non-linearly.
But generating and sampling these dense, potentially cyclic subgraphs sounds computationally hard.
Combinatorial explosion.
Totally. Brute force checking of all possible subgraphs is impossible. So V2 uses a random walk-based approach to sample subgraphs efficiently from their dense knowledge graph. Okay, sampling via random walks. But how do they ensure diversity? That they aren't just sampling variations of the same structure?
Good question. They use the Weisfeller-Lemon algorithm.
Ah, the graph isomorphism test.
Exactly. After sampling a subgraph, they use WL to check if it's isomorphic, structurally identical, to previously generated ones. By ensuring they only keep non-isomorphic connected subgraphs, they maximize the structural diversity in the SailorFog QA-V2 dataset.
Very clever. Ensuring each training example presents a structurally unique reasoning challenge. And they also focused on uncertainty.
Yes, beyond just masking information, they introduced a wider array of defined uncertainties. Things like ambiguity in definitions, conflicting information from different sources, temporal inconsistencies.
Trying to elicit more sophisticated reasoning skills beyond just filling in blanks.
Right, moving the agent towards being a knowledge synthesizer that can handle real-world messiness.
Okay, that covers the data generation side of WebSailor v2, denser graphs, cycles, richer uncertainty. Now, the other massive piece. Training scalability and stability. If WebShaper needed a clean gradient signal from good data,
WebSailor v2 needed a clean environment signal, despite using the chaotic real web.
how did they possibly achieve that?
Through a really smart dual environment strategy for the agentic RL.
Dual environment.
Yeah. First, they built a fully simulated environment. It uses a huge offline Wikipedia knowledge base.
Like a private, controllable mirror of the web's information?
Exactly. It's low cost, super fast, completely predictable. This became their sandbox for iterating on the RL algorithms, tuning policies, curating data, without worrying about real-world API flakiness. High-frequency experimentation.
But eventually the agent has to work in the real world. How did they bridge that gap from the clean simulation to the messy reality?
That required serious engineering for real environment robustness. They built a unified tool execution interface, basically, a sophisticated abstraction layer between the agent and the real web APIs.
An abstraction layer, what does that entail?
It's got several key components working together. There's a scheduling and management layer for tool calls, QPS constraints to avoid hitting rate limits, aggressive result caching.
Caching. So if the agent asks the same question twice, it gets the exact same answer, even if the live API might have changed slightly.
Precisely. Crucial for training stability. They also implemented automated timeout and retry protocols for network hiccups, and even service degradation strategies if an API becomes totally unresponsive.
Wow. So if, say, the Google Search API throws an error or slows down.
The agent doesn't see that raw error or delay directly. The abstraction layer handles it, maybe returns a cached result, or a standardized unavailable signal, or retries.
So the agent's perception of the tool interaction remains stable and deterministic, even if the underlying reality is chaotic.
That's the goal. To make tool invocation look like a deterministic and stable interface during training. It shields the RL process from the noise and volatility that usually plagues agents trained directly on the live web.
That sounds incredibly complex, but vital. Okay, with that stable environment, let's look at the training itself, the SFT plus RL pipeline. You mentioned RL for these tasks suffers from sparse rewards. How did they ensure the agent could even learn?
The key was the SFT cold start, the supervised fine-tuning phase before RL.
Right.
They first trained the model on trajectories generated by other open-source models solving similar QA tasks, using rejection sampling to get good examples.
Why is this pre-training so essential?
Because without it, the agent starts RL with a basically random policy. On these complex multi-step tasks, a random policy will almost never stumble upon the long sequence of correct actions needed to actually solve the task and get a positive reward.
The reward landscape is too sparse.
Exactly. The agent would just flail around, never getting the feedback needed to learn. SFT gives it a solid baseline policy. It can already perform basic multi-step reasoning competently.
So it starts RL already capable enough to explore productively and actually find those sparse rewards.
Precisely. SFT provides the necessary initial capability for meaningful exploration and convergence during the RL phase. It's a non-negotiable prerequisite for tackling these hard tasks.
Okay, makes perfect sense. Let's look at the results then. The cross-model benchmarking for WebSailor v2 sounds pretty game-changing.
The numbers are really impressive, yeah. Using their Qwen 330B A3B model node, only 30 billion parameters, they set new open-source records. 35.3 on BrowseCompEN, which is a tough browsing benchmark, and 74.1 on the GAIA text-only subset.
New state-of-the-art for open source, but the really striking part was comparing it to much larger models.
That's what really stands out. This 30 billion parameter WebSailor v2 model actually outperformed the massive 671 billion parameter DeepSeek v3.1 on several key benchmarks.
Wow, 30B beating 671B.
On BrowseCompEN, it was 35.3 for WebSailor v2 versus 30.0 for DeepSeek. On HLE, Humanity's Last Exam, 30.6 versus 29.8.
That is monumental. It really quantifies the impact of data quality and training stability.
Absolutely. It strongly suggests that how you train the quality of the data structure, the stability of the environment, can be more important than just throwing more parameters at the problem. A meticulously trained agent, 20 times smaller, got better results.
That has huge implications for accessibility and compute costs in the open source world.
Definitely. And how did it stack up against the best proprietary systems?
On the DeepResearch bench, specifically designed for these complex tasks, WebSailor v2 scored 48.9.
Okay. And the proprietary soda?
That was Gemini 2.5 Pro DeepResearch at 49.7.
So incredibly close, almost identical performance.
Yeah, and the authors themselves suggested that tiny gap might not even be about core reasoning ability.
Right. They mentioned they deliberately focused less on polishing the stylistic quality of the final generated report, unlike some big proprietary models.
And focused intensely on the core logic, retrieval, and synthesis. So the reasoning might be on par, just the presentation slightly less refined.
Which is a fascinating trade-off.
Now, let's quickly touch on the agent scalar findings regarding training stability. They use that two-stage SFT RL approach as well, right? What did agent scalar add to the picture?
Agent scalar was really about systematically studying this two-stage process and its stability. They used a benchmark called taught-to-bench to measure robustness.
Taught-to-bench. Designed for consistency checks.
Yeah, it tests how well an agent performs on the same task across repeated trials, where small variations might trip up a brittle policy. The agent scalar work confirmed that both stages, stage 1 for general foundation, stage 2 for specialization, significantly boosted performance.
And they used the pass at T metric?
Right. Pass at K measures the success rate over K attempts. Agent scalar models showed much higher pass at K scores than the baseline QE models.
Meaning they were more reliable and more consistent across runs.
Exactly. It shows that the focus on data quality and environmental stability really translates into a more robust, less flaky agent policy.
But even with all these advances, better data, cycles, stability, the fundamental difficulty of long horizon tasks didn't just disappear, did it?
No, absolutely not. The agent scalar analysis, figure 5 in their paper, confirms this quite clearly. There's still a persistent negative correlation between the number of tool calls needed for a task and the agent's final accuracy.
So the longer the chain of reasoning and tool use,
the more likely the agent is to eventually make a mistake. Even these advanced agents struggle significantly when tasks require, say, 15 or 20 plus distinct tool interactions. Maintaining accuracy over that many dynamic steps remains a core, unsolved challenge.
Interesting. And one last detail, the entropy dynamics during WebSailor v2's RL phase. What did that show?
They observed that the RL policy's entropy stayed high. It oscillated but didn't converge sharply downwards.
Which is different from typical RL in closed environments where entropy drops as the optimal policy is found.
Right. In a fixed game or simulation, you expect convergence to a low-entropy, deterministic policy. The fact that entropy stayed high here is thought to reflect the inherently non-stationary, complex nature of the real web environment.
Even their stabilized version still has underlying variability.
Exactly. The observations don't follow a perfectly fixed distribution. This constant subtle shifting prevents the policy from locking into one rigid strategy. Instead, it fosters a more adaptive, robust policy that retains a capacity for exploration.
So the high entropy isn't a bug, it's potentially a feature, reflecting adaptation to a dynamic world.
That seems to be the interpretation, yeah. The environment itself provides a kind of natural exploration pressure.
Okay, let's synthesize this. Across WebShaper and WebSailor v2, we've seen a clear path forward for open source DR agents. It involves formalizing knowledge structures like KPs,
Rigorously controlling data synthesis, whether through layer-wise expansion or dense cyclic graphs and complexity filters.
and crucially, engineering highly stable training environments, possibly using dual simulated real setups with abstraction layers.
Absolutely. And if there's one central takeaway, maybe a philosophical one from all this research,
What would it be?
it's that the quality and consistency of the training experience, the data's structure and diversity, the environment's stability, seem to be incredibly powerful levers. Arguably more critical right now than just the specific RL algorithm used or even the raw parameter count of the model.
The empirical results bear that out. Smaller models, trained meticulously, are achieving performance once thought exclusive to massive systems.
It really reshapes the landscape, showing that smarter training can potentially beat brute force scaling, at least for these complex agentic tasks.
So we end, as always, with a thought for you, our listener, to ponder. We heard that WebSailor v2 deliberately deprioritized the stylistic polish of its final reports, focusing instead on core reasoning, retrieval, and synthesis, which left a tiny gap compared to proprietary models known for smooth output.
A conscious engineering choice.
Given that the core reasoning seems largely solved, or at least massively improved, where does the next major push need to happen? Is the priority now to build that sophisticated presentation layer on top, closing the stylistic gap to make the output more user-friendly or polished?
Or is the more fundamental, perhaps more difficult challenge to take the environment stabilization techniques demonstrated by AgentScaler and WebSailor v2 and apply them to integrate even more complex non-web-based tools like code execution, database queries, scientific simulators into these agents? Where should the focus be next? Abstraction and presentation or deeper tool integration? Something to think about.